Good. We have covered as much as we could on fission systems, and we suggested that we cannot continue on the existing uh, uh, type of a once-through fuel cycle. It is being continued because the uranium-235 resources are plentiful and they are cheap, but at some point, say within 50 years, we'll start running out of the uranium-235. So we'll have eventually to switch to the thermal reactor type of fuel cycle. And in the long term, we need to switch and establish the breeding in the fission systems. Breeding would be a necessity in the long-term application of nuclear power generation. However, there is a competing approach, which would be fusion energy. So in the coming lectures, we will concentrate on the learning about how fusion could become part of our future in general. So we go to our web page and identify the area where we talk about fusion energy per se. There are several chapters in that part of the course, and I'll try to squeeze them into two lectures and then cover other topics of interest from the applications in general. So let us start with an introduction on plasmas and fusion reactions in general. The interesting aspect of it is that fusion reactions are, you could say, the mother of all energies, like our energies on Earth, whether it is solar energy, wind energy, are all nuclear energies in their origin. Even when you use fossil fuels, when you use coal, we use natural gas, or we use petroleum, that is fusion in our star, the sun. And notice that the energy that we get from the fossil fuels are basically dead plants and dead animals, plants for coal, dead animals for petroleum and natural gas maybe. And in fact, they are stored nuclear energy. There were initially solar energy that grew those plants, trees that turned into coal, or grew planktons and fish in the oceans that eventually turned into petroleum. So the origin of all energies in the universe is nuclear. You notice here a picture of the surface of the sun. That's a NASA photograph. The sun itself is a monumental fusion reactor in which hydrogen is being burned and using lots of reactions that have catalysts like nitrogen, for instance, or carbon. And in the end, the hydrogen is turning into helium in our star, the sun. Notice that the nuclear energy follows our famous mass energy equivalence equation, so-called Einstein equation. And basically, the dream of humanity is maybe to be able to implement fusion energy in competition with the breeding in fission type of reactors. The fusion type of energy release has been successful, in fact, in thermonuclear devices, thermonuclear weapons. We know how to generate fusion energy there, but it is not in a controlled fashion. In a controlled fashion, we need to break even in the energy to create a plasma and to generate fusion energy. We need to invest energy. And like any kind of energy system, you invest energy. Let's take petroleum, for instance. You explore for petroleum, you drill a well for petroleum, you pump the petroleum out, you refine the petroleum, you transport it to the centers of where it's being consumed, and you hope that in the end, the energy that you get out of it exceeds the energy that you invested in extracting and producing it. The situation in the control of fusion energy resembles that situation, in that to create a plasma where fusion could occur on Earth, not in the stars. It occur in the stars all by themselves because of the mass of the stars. And you'll have to find that we find so far that we are still spending more energy creating the conditions for fusion than we are getting out of it. The day that we reach break even, meaning that energy in should be equal to energy out in creating fusion conditions, then we are on the road to achieve energy. The research in fusion energy has been quite challenging. I quote here Nobel Prize laureate Alfvén, a Swedish famous scientist, quote, "Since thermonuclear research started with Zeta, tokamak, accelerator, these are names of fusion devices, not to forget the perhapsatron, plasma theories have absorbed a large part of the energies of the best physicists of our time. The progress which has been achieved is much less than was originally expected. The reason may be from the point of view of the traditional theoretical physicist, a plasma looks immensely complicated, and that is true. We may express this by saying that when, by an immense numbers of vectors and tensors and integral equations, theoreticians have prescribed what a plasma must do, the plasma, like a naughty child, refuses to obey. The reason is either that the plasma is so silly that it does not understand the sophisticated mathematics, or it is that the plasma is so clever that it finds other ways of behaving, ways which the theoreticians were not clever enough to anticipate. Perhaps the noise generation is one of the nasty tricks the plasma uses in its IQ competition with the theoretical physicist." Here, Alfvén is trying to be funny here, but that is really a description of the current situation. Another scientist, Perrat, quote, "The universe is predominantly matter in its plasma state, and electromagnetic forces are stronger than gravitation by 39 orders of magnitude." I repeat here, electromagnetic forces are stronger than gravitation by 39 orders of magnitude. And when people talk about the missing mass, I have suggested in a previous chapter that the missing mass problem that plagues astronomy at every facet in its size hierarchy may not exist at all when you take electromagnetism to augment gravitation. If the properties of plasma are the same everywhere, from the micrometer dimension structures produced in the dense plasma focus, that's a fusion device, to the Hubble distance, then not only can our knowledge of the universe be improved, but also a backflow of data. Oops, somehow it messed up itself. Oh boy. Okay, we are back in business here. I have instability in the internet. Then not only can our knowledge of the universe be improved, but also a backflow of data to laboratory experiments can be expected. So what is a plasma? Again, when we deal with plasmas, we are dealing with some biological analog, like when we dealt with fission, we dealt with analogs of bacterial population. A gentleman, a scientist, Langmuir, introduced the terminology or the term plasma in 1928 in a paper on the oscillations in ionized gases. And he states we shall use the name plasma to describe this region containing balanced charges of ions and electrons. So a plasma is a state of matter where we have a balanced mixture of ions, like ions of hydrogen maybe in the sun, and electrons. His adoption of this biological term may be related to the behavior of the plasma, almost like a living cell. It has a sheath that surrounds it, the same way as a cell has a membrane that surrounds it on the outside. So a plasma is known to protect itself from the environment by a double layer of plasma sheath, in the same way that a living biological cell protects itself with a cell wall from its environment. So here are the examples of plasmas that we see in our universe. This is a solar flare. You could see here that the magnetic field of the sun protrudes over the surface of the sun, and it goes up at one point and then comes down at another point, and charged particles rotate around the magnetic field lines. If you have a chance to look at sunspots on the sun, you'll always find that sunspots occur in pairs. You have one and two next to each other, which is really in the plane, a description of how the magnetic field leaves the sun's surface and then comes back. It's almost like a wire coming off from the sun's surface. On Earth, this is what we are trying to achieve in the laboratory. This is a pellet that contains some fusion material, maybe deuterium plus deuterium, or deuterium plus tritium, both isotopes of hydrogen. And basically a fusion can occur in the experimental lab. And another form of plasma, we said that it permeates most of the universe, is lightning. Lightning that we see in the sky in thunderstorms is definitely a plasma. The discharge of the very high electromagnetic field, it's an electric field in that case, creates a plasma, a mixture of ions and electrons in general. So plasmas are very, very common in our universe. One important aspect of plasmas is a solar wind that affects the Earth. And in that case, the Earth is fortunate enough to have a defense against it in the magnetic field of the Earth created by radioactivity in the center, around the center of the Earth, because the center of the Earth, as we know, is a solid. The outer core is liquid. The rotation of that liquid creates the Earth's magnetic field that protects us from too much of a good thing, like the solar radiation. Mars has not been that fortunate. Mars does not have a magnetic field, and the solar wind is thought to have depleted its atmosphere and evaporated its water over time in general. So the Earth is fortunate to have protection through its radiation fields. And let's us just remember that plasmas are common in most of the universe. Interstellar gas is a plasma. It has a very high temperature, in fact, 10,000 kelvins. This is K for kelvins. It has a low density. It has one particle per centimeter cube. If you go to the solar corona, or the surrounding part of the surface of the sun, that's 1 million particles per centimeter cubed, much more dense. In the ionosphere of the Earth, it's the same as a solar corona. The ionosphere surrounds the Earth, and it's a region of the Earth where radio waves get reflected back and allow us communication over long distances. A Q plasma and a dense plasma, you could see the density becomes higher and higher by orders of magnitude. If you have an arc discharge in welding, that's 10 to the 14th particles per centimeter cube. And the thermonuclear or a dense hot plasmas that we create in the labs or in thermonuclear reaction is very, very dense plasma, 10 to the 16th particles per centimeter cube. And also very, very high temperature. Look at the solar corona temperature, 1 million Kelvin. We create in thermonuclear reactions 100 million kelvins. And this is associated with very strong magnetic fields. Interstellar gas has a very low magnetic field, 1 millionth of a Gauss, whereas in thermonuclear reactions that we create in experiments and thermonuclear devices, that's basically 100,000 Gauss compared to 1 millionth of a Gauss. So plasmas are part of the universe around us in general. And as I suggested, the solar wind could destroy life on the surface of the Earth if we didn't have the protection of our Earth's magnetic field. As the solar wind is trapped in the Earth's magnetic field at the poles, North Pole and the South Pole, the particles from the sun, protons and electrons, rotate around the magnetic field lines. They come to the surface of the Earth, they interact with the nitrogen and oxygen in the atmosphere, And we get those very beautiful looking northern lights or aurora borealis in the northern hemisphere. This is the Earth's surface here, or the aurora australis in the southern atmosphere. So this is, if you travel over the summer to northern Michigan, Traverse City, for instance, you could already see those on some nights when the sun is very active. Those northern lights are a beautiful view, and this is how the Earth is protected by several radiation shields. And you'll find that satellites and astronauts would have to go through them as they're being launched. So they become subject to a very large dose of radiation. But the satellites and the space station, the astronauts are placed outside of those radiation belts. You could see here, this is they can extend up to 6 Earth radii, and this is where the basically the shape is toroidal. Think about a torus here surrounding the Earth, and this is a simulation. Results of a simulation, you'll find that the Earth's magnetic field at the top of the Earth in the North Pole, the magnetic field gets into the core of the Earth and exits from the other side. But the Earth has those two regions of the inner Van Allen belt. The person who discovered them the radiation belts are named after him. And there is an outer radiation belt. And this is the orbit for our electrical engineers of any geosynchronous satellites. And that is quite a long distance. That is about 22,000 miles or 30,000 kilometers. And what happens is, as we have known earlier, that in a magnetic field, a charged particle rotates around the magnetic field line. That's a Joule equation that we dealt with when we looked at the enrichment of radioisotopes using electromagnetic or the Calitron effect. The rotation of the particles from the North Pole to the South Pole generates what people like to call the banana orbits, because they take the shape of a banana, but the particles move from the North Pole to the South Pole. The magnetic field lines there are some kind of squeezed together. So you find that the charged particles reflect back and forth between the North Pole and South Pole, with some of them leaking to the surface of the Earth and creating our aurora borealis and the aurora australis. Shouldn't we have that magnetic field where the Earth is protected, the radiation basically is trapped, and that inner Van Allen belt surrounding it in the shape of a torus and the outer radiation belt, you find that the intensity of the radiation in counts or the, per second, if you send a rocket as a probe and measure the radiation field there, the inner one can have 10,000 counts per second. So you cannot have astronauts, you cannot have electronic equipment like satellites within the area of the Van Allen belts surrounding the Earth. We'll come back to this idea of the banana orbits, where the magnetic field lines are squeezed together, and then the charged particles reflect when you squeeze the magnetic field lines to suggest a design of magnetic confinement types of reactors, where we confine the isotopes of deuterium and tritium, or deuterium and deuterium, and cause magnetic fusion. So we'll take that into account later on. For the benefit of our electrical engineers, you find that we position our satellites, as I suggested, the geosynchronous orbit. NASA's Solar Dynamic Observatory is at 22,000 miles. That's outside the range of those magnetic field, the radiation belts surrounding the Earth in general. All right. So, however, astronauts, as they're being launched into space or retrieved from space, have to go through those radiation belts, and in that case, they need to be protected against radiation in general. In the Van Allen belts, we said we have two zones: an inner zone, primarily composed of electrons and protons, and basically at an altitude from 3,600 to 5,400 kilometers. And the intensity is 2 trillion particles per centimeter square per steradians, or that's a unit of solid angle. The outer zone is farther out, 16,000 kilometers. That's about 12,000 to 19,000 kilometer. And you find, again, electrons and protons. So it's a plasma there that is really confined there with a threshold energy of the particles of, say, 20 kilo electron volt to about 200 kilo electron volts. So we are going to try to use this natural phenomenon as some kind of an inspiration for designing future fusion reactors. Now let us talk about the process of fusion. How do we achieve fusion? First, we are going to create a plasma. We are going to heat the atoms. As you heat the atoms, you impart enough kinetic energy to the electrons to be stripped out of the atom, and you end up with a mixture of electrons and ions. In that case, you have a plasma. In that case, we try to get the ions to fuse together, to combine together, like what happens on the sun. We'll look at the equations that happen in the stars in general, and our sun. And yeah, they have to overcome the repulsion between two charged particles. We know that through the Coulomb reaction or the Coulomb barriers, equal charges repel and opposite charges attract. So if you want two positive ions to fuse together, they'll have to overcome that repulsion between the two ions. That is a Coulomb barrier, and some people have basically visualized it as being a volcano. So think about the nucleus of one ion being a volcano with a well inside the volcano. And when a charged particles wants to come into and fall into the well of the volcano, it has to overcome that height. So the energy of the particle come in should be equal to the height of the Coulomb barrier. Otherwise, a charged particles can come in, either get reflected back from the Coulomb barrier volcano, if you want to call it, or it can get deflected here. So overcoming the Coulomb barrier is necessary for achieving fusion. And we can calculate how much that energy is, the magnitude of that energy, by taking the diameter of an atom, in that case, actually, of a nucleus. We said that is proportional to the mass number of the nucleus. So that's A to the 1/3 power in centimeters, 5 × 10⁻13 centimeters. So if we write the expression for the charge of the nucleus, Z1, the number of protons in it, multiplied into the charge of the electron, multiplied into the incoming ion, its charge Z2, multiplied by the electronic charge. This is now like Q1 multiplied into Q2. You have seen that equation for the Coulomb repulsion earlier, divided into 4 pi r squared. We are ignoring the 4 pi here. And the force between the two ions, in that case, in dynes, the unit of force in the CGS or the conventional system of units, can be calculated. So we can get the calculation of that number. We know that the charge of the electron in electrostatic units is 4.8 × 10⁻⁻⁻⁻. And the energy that we need for a collision between those two particles would be Z1, Z2, the square of the electronic charge divided into the distance between them. Notice that the force is proportional to 1/r squared in that equation here. That's 1/r squared, the force, but multiply force by distance, you get work done, and work done has units of energy. So in that case, you divide by the distance between the incoming nucleus and the static, let's consider a static nucleus. If we take R1 is equal to R2, maybe the two isotopes of hydrogen or two deuterium or tritium, you'll find that you can get an equation here from the radius of the nucleus, 5 × 10⁻13, a to the 1/3 power. And we can get an estimate of the energy in ergs, unit of CGS, system of units of energy, Z1 multiplied into Z2, the charge of the the charges of the two interacting ions, in that case, divided by the mass to the 1/3 power. That's a volumetric kind of effect, as you could see here. And of course, we substituted for the units as 1 MeV being 1 million electron volt being 1.610 to the -6 erg. So we can really plug in the numbers there, and we get an estimate of the energy that we need to overcome the Coulomb repulsion. If we take the example of hydrogen, so Z1 is equal to 1, Z2 is equal to 2, and A is equal to 1, we get an estimate as the minimum energy that we need for fusing two nuclei to overcome their Coulomb barrier is 0.3 million electron volts. That's a very high energy, very, very high energy. So we are lucky enough that the quantum mechanical effect happens to not needing that 0.3 million electron volt to get over the volcano of the nucleus in Coulomb repulsion. You'll find that those incoming ions undergo some process in quantum mechanics of penetration of the barrier. So the incoming proton acts like a wave and can penetrate the barrier without having to overcome it. So instead of that 0.3 million electron volt, the penetration can happen at 10 kilo electron volt instead of the 300, in that case, kilo electron volt. This process is called tunneling. And the tunneling basically is dependent upon in generating thermonuclear reactions on Earth. I'm just trying to show you here that tunneling or quantum mechanics or wave mechanics play a role in overcoming the Coulomb or the nuclear barrier penetration in general. What happens in the stars and in the sun is something that can become for us also some inspiration on how to achieve fusion on Earth. And the reactions that happen in the stars have been described by scientists Hans Bethe and Critchfield in 1938. And another two people, Lawrenson and William Fowler, further developed the theory. So they suggest basically that in the stars, the hydrogen nuclei, remember this is a nuclear reaction, not a chemical reaction, can basically fuse together and then dissociate back again. Occasionally a proton and turns into a neutron and a positron, and a neutrino, not an anti-neutrino, is emitted. Some other fusion reactions occur between isotopes of helium. Helium-3 plus helium-3 gives us a helium-4 plus a hydrogen atom. So all these are different reactions that they studied for the fusion in the stars in general. However, the main reaction that happens is that two hydrogen ions fuse with two hydrogen ions. They give us two deuterons, which is an isotope of hydrogen containing an extra neutron. Two positrons are emitted, two neutrinos. It's not anti-neutrino. Anti-neutrinos are emitted when a negative electron is emitted by definition, and that releases 2.38 million electron volts of energy. While the deuteron here now finds a hydrogen nucleus, so it fuses with it, produces helium-3, two gamma photons are emitted. Eventually they reach us on Earth as solar radiation. And that helium-3 fuses with another helium-3 nucleus, leading to the production of helium. and another proton. If you cancel the protons from both sides, you find that they act as a catalyst, and the helium-3 acts as a catalyst too. You get that 4 hydrogen nuclei fuse together and turn into helium-4, 2 positrons, 2 neutrinos, and 2 gamma photon. And each one of those, each reaction that fuses 4 atoms of hydrogen produces 26 million electron volt. And this is the main reaction we call it the proton-proton chain. It's basically composed of 3 reactions. There is more detail to it in that some other elements in the star come into play. Some reactions do not produce helium-3. The helium-3 in that case combines with helium-4 and creates beryllium-7. Beryllium-7 interacts with an electron, produces lithium-7, and lithium-7 interacts with a proton and gives us also 1 atom of helium-4. That's basically a different way in the branching of the proton-proton reaction chain. That beryllium-7 also can start interacting in a different way. It can interact with a proton, giving us boron-8. Boron-8 emits a positron and turns into, and that's boron, it turns into beryllium. Beryllium itself decays and turns into 2 nuclei of helium-4. If you add those reactions again, cancel both sides, the catalysts in the reactions, 4 hydrogen atoms like here turn into helium-4. There's 2 reactions. There are different chains that occur at lower probabilities, but overall the energies, those reactions occur in the stars as described by Hans Bethe and Critchfield. All right, now this is a reaction that happens in stars that are small masses like our sun. And these reactions occurring in stars with central temperatures less than 20 million Kelvin. And this is basically designated as the proton-proton chain. You notice here that the end result is that with catalysts occurring, the helium-3, the beryllium-8 and beryllium-7, the boron, and so on, boron-8, in the end, 4 hydrogen nuclei are turned into helium-4. That reaction does not occur on Earth. So we are going to think about other reactions. Basically, their time constant is in the billions of years, the age of stars. On Earth, if you want to produce energy from fusion, we have to think about faster reactions between deuterium and deuterium, or between deuterium and tritium. For stars that are larger in size, main sequence stars of a large mass, which also have temperatures in the 200 million Kelvin, a different reaction occurs, and it's called the carbon-nitrogen chain. And that has an interesting terminology here, because we know that the carbon-nitrogen reactions occur in biological systems. But let's look at the reaction there. You find that in the main sequence stars, carbon-12 exists. So you find that the hydrogen fuses with carbon-12, produces nitrogen-13. Nitrogen-13 emits a positron and turns into carbon-13. Carbon-13 interacts with a proton, gives nitrogen-14. Nitrogen-14 interacts with a proton, gives oxygen-15. Oxygen-15 emits a positron, turns into nitrogen-15, and that one fuses with hydrogen. The end result, if you cancel the catalysts on both sides, you end up with 4 hydrogen nuclei turning into an alpha particles. That chain, or the carbon-nitrogen fusion chain, has some other ways of occurring with lower probability. So the nitrogen-15 can interact with a different way, and we get a subset of that particular reaction, much more complicated. And then the oxygen-17 can also interact differently with a proton, leading to another set of chain reactions. In the end, here you could see 8 hydrogen nuclei are producing 2 helium-4 nuclei. So even though there are reactions with other isotopes of oxygen, fluorine, carbon, nitrogen in the stars, but in the end result, hydrogen is being turned into helium-4. What happens as a star burns most of its hydrogen? You'll find that older stars now have lots of helium-4, and they burn their hydrogen. You'll find that the helium-4 now starts burning. So the helium-4 nuclei fuse together, give us beryllium-8. This is a process of what is called nucleosynthesis. This is how different elements in the periodic table are being formed in the different stars of different ages. For instance, that beryllium-8 would now fuse with helium-4, and it turns into carbon-12. So some of the heavy elements are formed once the star burns most of its supply of hydrogen. Well, what if now they have formed lots of carbon-12 and have depleted their supplies of hydrogen and helium? Oh, they start burning carbon itself. So you find that one nucleus of carbon and another nucleus of carbon start producing a heavy element, magnesium-24 or sodium-23 or neon-20. Well, when they end up burning most of their carbon, they start burning their oxygen. So you find the oxygen with oxygen producing silicon, sulfur, phosphorus. However, that didn't reach the level of the uranium. And we'll see in a moment that uranium is a different process than the process of nucleosynthesis here. So silicon now, a silicon star that has burned its hydrogen, helium, carbon, and so on. Silicon starts interacting with silicon, producing nickel, cobalt, and some iron. And some other reactions occur also, like gamma alpha reactions, where gamma radiation interacts with the isotopes that are being built up with neon, for instance. It produces oxygen and helium-4. There are also reactions that occur that are called the alpha gamma reactions. And we can learn from these reactions maybe in the design of future fusion reactors. An alpha particle can fuse with magnesium-24, producing silicon-28. There are reactions that occur between a proton and gamma reactions. And this is shown here, a proton proton interacting with carbon-12, oxygen-16, oxygen-17. So this is a process of nucleosynthesis. And in that case, we can identify how maybe up to iron is being formed in the stars, or silicon is being formed in through the nucleosynthesis in the star. However, when we talk about the heavier isotopes of uranium and thorium and so on, our state of knowledge suggests that it is really another process in which a star has burned up all its nuclear fuel. And as you burn the nuclear fuel, you are generating energy, that energy in the form of radiation. And the star has another form of energy acting on it, which is the inertial energy or the gravitational energy. So they balance out in a star that is burning its fuel. What if the star runs out of fuel? Then the gravitational force takes over, the star collapses upon itself, and we create what's called the supernova. Supernovae are processes where the stars implode or basically burn themselves out. And in the process, the nuclei come very close together. And you'll find that in that case, the heavy elements, the thorium, the uranium, are being formed. Why are we studying this? Because again, humans try to imitate nature. And other than trying to confine a plasma using an imitation of the Earth's magnetic field, we try here to generate a plasma by imitating the process of supernovae. Our best state of knowledge is that our Earth, in fact, the rocky planets, Earth, Mars, and Venus, and are all created into a monumental kind of process where supernovae were created. There are two types of supernovae. One is called the type 2 supernovae and supernova, and we have pictures of them. They occur every once in a while. There is a type 1a supernova, and they have been observed. So this is the CASA supernova. It happened in the year 2000. And as you could see here, the supernova, the star exploded. It creates a brightness in the sky. And then the results of the explosion or the implosion, in fact, the supernova are now heavy elements that get dispersed into stellar space. And the solid planets and maybe the asteroid belt has been a result of that process where those remnants of an exploding star have been grabbed by the sun's gravitation. And well, that's what we owe our livelihood or existence to, a supernova that happened in the long past. Some astronomers in backyard astronomers have been observing those supernovae. Usually the supernova goes through a process of what's called the light curve. Initially, it's very bright. The brightness increases, and then it decreases as basically gamma rays and X-rays are emitted. So this is the several months after an explosion of a supernova. Okay, we are studying these processes of the Earth's magnetic field and of supernovae because that will be the basis of what scientists are trying to create, say using inertial confinement, basically trying to fuse deuterium and tritium in the same way that a supernova happens in the stars. And they're trying to also create fusion in the same way by trapping the particles in a magnetic field in the same way that charged particles from the sun are trapped in magnetic field. And we may think about other physical processes that we can that happen in nature that we can imitate and creating fusion in a controlled manner. So this is another picture here of SN. SN stands for supernova 2008. That happened in 2008. Another supernova happened earlier than it in 2007. And you look at it with satellites, not just in the visible spectrum, but you also look at them in the different parts of the electromagnetic spectrum. And this is a satellite launched by NASA. It's called the Swift Observatory. On the top, basically you get an X-ray image only. So this is what we see as X-rays from that SN 2008. That's in the year 2008, recently, in fact. And but then if you look at the visible part of the spectrum, that's what you see here as bright in the star. That's a 2007 supernova and supernova 2008. So in fact, there were a picture in that here in the visible light before that SN 2008 had exploded, actually imploded. This is another picture as a function of time in 2014, 2015 of one of those supernovae occurring. We see them and they are usually detected and seen first by backyard amateur astronomers who equip themselves with a nice telescope. And you could see that's the light echo reflection from reflection of the energy generated from the supernova by dust in the atmosphere. That one happened in 2014 in a galaxy called M82, 11.4 million years away. And that was called, that pictures have been caught by the Hubble Space Telescope. Okay, so what happens in the supernova? You find that now the heavy elements in a star that has burned into hydrogen and helium, you'll find that it starts burning carbon, oxygen 16, neon 21. But then only we get there heavy elements up to magnesium and sometimes up to iron. But in And we call that process the process of nucleosynthesis. But in fact, supernovae are the basis of the heavy elements. Some people suggest that not only supernovae are sources of the heavy element formation, but nucleosynthesis or the synthesis of nuclei can also happen between neutron stars that are colliding or in what's also called gamma rays bursts. And we covered the topic of gamma rays bursts in the chapter of gamma rays interaction with matter. All right, so we know then that fusion reactions are the basis of the mother of all energy in our universe. It happens in our stars. And we know that primarily it's hydrogen plus hydrogen, generating an energy of about 1.4 million electron volts per reaction. Notice that it is not negative electrons produced, but positrons. We may come to that topic later on. But the time constant or characteristic time of this hydrogen plus hydrogen reaction in the star is 100, not 1,000 million, but 100 trillion years. Wow, so it's a very long time constant. However, we know that on Earth, if we try to fuse other isotopes of hydrogen, instead of 1H1 plus 1H1, we try to fuse one deuterium nucleus plus one deuterium nucleus, producing helium-3. Oh, that takes only 0.0003 seconds, 1/100,000th of a second compared to 1 trillion years. So, and another branch of that DD reaction, we call this branch here the neutron branch because it produces helium-3. We call this 1D2 plus 1D2 the proton branch because it produces a proton. And if you balance the reactions, you'll find that tritium, another isotope of hydrogen, is produced. So if we want really to achieve something similar to what happens in the stars, we need reactions that have a very short characteristic time. And in fact, this is happening in thermonuclear devices, but we don't have it yet in a fully controlled manner. Other reactions, and look at this one, the D plus T characteristic time is even much shorter than the DD reaction here. That's 3/100,000th of a second. That is 1.21 millionths of a second. And you can even fuse tritium with tritium. And in that case, you produce an alpha particle. I have a student work, write a thesis on that reaction. It's a reaction that multiplies neutrons. It creates more neutrons for us. I don't know. We don't know really. Somebody can study it as a thesis, maybe a physics person or a chemical engineering person. All right. So the fusion of the light nuclei in a plasma created in devices where we try to imitate nature in terms of either inertial confinement, like the neutron stars colliding or the supernova occurring. This would constitute a cleaner source of energy than fossil fuels and fission fuels. They would not release greenhouse gases released by fossil fuels, obviously. So they're carbon-free type of a process. They will not release either the fission product generated by fission fuels, which is a problem in terms of some people objecting that they are disposed of in their own backyard. The ashes of the fusion reactions would primarily be like in the case of the star's helium nuclei. Oh, we can use it in balloons and it's an inert gas, helium, as we know. So that is not any concern to us in terms of environmental damage. So this is basically why we look at nature in terms of fusion. Both the trapped particles in the Earth's magnetic field will be the basis of what we are going to call magnetic confinement fusion, and the supernovae in the formation is going to be the basis of what we are going to call inertial confinement fusion. And in any kind of engineering or physics kind of endeavor, we try to imitate nature. Nature has been there longer than us, and we can learn from it. I'll go to the chat room if you have any questions. Otherwise, I'll continue covering the topic of fusion energy in our future. All right, we won't lose our time. We will go back and cover the next chapter in fusion. So what is the next chapter now? The next chapter, obviously, the fusion concept. As I suggested, we try to imitate nature in terms of trying to achieve fusion in a controlled manner. Some people suggest, oh, well, that it is not feasible. No, and we know it happens in nature. So in the first place, we can achieve it in general. We repeat the notion that the universe basically is primarily plasmas. This is a nebula. It's called the Cat Eye Nebula. It's a beautiful picture there provided to us by NASA. As I suggested, on Earth, if you want to achieve fusion, we have to depend on some isotopes other than hydrogen per se. You cannot fuse hydrogen because its characteristic time or the reaction cross-section, in fact, is very, very low. Even though it can happen in the stars, it would take a long, long, long time to happen on Earth. So we depend on other isotopes like deuterium or tritium. And in that case, we know that if you take hydrogen on Earth, the deuterium to hydrogen ratio is 160 parts per million. Or if you take the deuterium, the inverse of it, the deuterium to hydrogen ratio is 1.5 10 to the minus 4. In other words, in 10,000 atoms of hydrogen, you'll find about 1.5 atoms of deuterium. And think about our oceans, and that constitute 70% of the Earth's surface. They contain H2O, but some of the molecules of water contain, according to that proportion, of 1.5 10 to the minus 4 or 1.5 in 10,000 nuclei of deuterium. So we have an unlimited supply of energy there on Earth in water. We would be burning water to produce energy if we can harness the use of deuterium, for instance, for producing fusion energy rather than fission. It can be used in electrical power production like fission is used today, but there is a shortage all over the Earth of freshwater supplies rather than a shortage of electrical power, even though some countries, you can read about it in Lebanon, for instance, they are unable to produce electrical power all the time, and so their society is totally collapsing without electrical power for their hospitals or other human activities. We can also use fusion to produce hydrogen, store the energy of fusion in the hydrogen process, and use the fuel cells, as we have studied earlier. In addition, to electricity from renewables, solar and wind, and the hydrogen becomes a replacement for batteries. It would be an energy carrier, and when we use it in fuel cells in a new transportation system that doesn't use hydrocarbons and change our climate, then fuel cells using hydrogen can be the basis of a future transportation system. Fusion can be also used with its high energy neutrons, as we'll see from the DT reaction, to deactivate the reactor waste that we produce in fission reactors. Or we can do the opposite. We can absorb neutrons from fusion into uranium-238 and produce fissile fuel like plutonium-239. Or we can absorb neutrons. That would be a hybrid between fission and fusion in that case. In thorium-232 and produce fissile elements like uranium-233. And fusion would be the way to really build a rockets that have a very high specific impulse or impulse per unit mass for interstellar, not just trips to Mars, but also maybe leaving our solar system. So that would be in the future for our children and our grandchildren. There has been a historical development, as I suggested. You can read about it in detail, but definitely there are huge advantages for humanity to develop fusion energy as an alternative to using fission. The fuel supply is abundant. Well, it's our oceans, and if we run out of hydrogen in our ocean, we can go and mine hydrogen from the asteroid belt or from Jupiter. Jupiter is all hydrogen, in fact. When we design the fusion reactors, the design is non-critical, so it cannot reach a critical mass like what could happen in fission reactors. It doesn't create air pollution. It doesn't create high-level nuclear waste. And in fact, it doesn't produce much weapons material unless it is designed to produce weapons material. As I suggested earlier, we will take our ideas from nature in what happens in the stars. We cannot use a hydrogen plus hydrogen reaction that happens in the stars, but on Earth, we have the deuterium in the water in our oceans. So if we extract the deuterium, and it's very possible, we have seen how to produce heavy water, for instance, in the chapter on isotopic enrichment. Deuterium plus deuterium, as we have shown, has two branches. One branch that produces a neutron 50% of the time, and another branch 50% of the time also that produces a proton. So in that case, when a proton is produced, you balance the reaction, you get tritium. And if you balance the reaction neutron, deuterium plus deuterium, 50% of the time you get helium-3. So, and you can basically build a nuclear reactor based on that deuterium plus deuterium. However, something interesting happens is that tritium is produced, and tritium can also fuse with deuterium. So in that case, you get another reaction, deuterium plus tritium, gives you an alpha particle plus a neutron and produces 17.6 million electron volts. And we have balanced that reaction in the past, and you did calculate as an assignment its Q value. That helium-3 that is produced there can also find a deuteron and fuse with it. And you get, in that case, two charged particles, a helium-4 nucleus and a proton. So if you have a plasma made out of deuterium, you'll find that 1, 2, 3, those 4 reactions can all happen at the same time. And we call this a catalyzed DD fusion reaction. So now I wrote those 4 reactions together, 1, 2, 3, and 4. And if you add on the left-hand side 6 deuterons, 1, 2, 3, 4, 5, 6, you'll find that they fuse. And in the case of the stars, it's 4 hydrogen nuclei turning into helium-4. But here, our 6 deuterons turn into helium-4 plus 2 neutrons plus 2 alpha particles. We can divide both sides of that equation by 2. So you find that 3 deuterons turn into 1 proton, 1 alpha particle, and 1 neutron, and basically 21.5 million, half the amount here because we divided into 2 of energy produced. Notice that each reaction, if you calculate the Q value and use our momentum allocation equations, you can calculate the energy of each one of those particles from those reactions. But the end result is basically a reaction that imitates what happens in the stars here on Earth, with tritium canceling from both sides, helium-3 canceling from both sides, so they act as catalysts. And that's why we call this type of a chain reaction a catalyzed DD, deuterium plus deuterium, chain reaction. So in that case, for each deuteron, we can produce 43.2, the total energy divided into 6, 7.2 million electron volts per nucleus of deuterium. It is not as much as 200 million electron volts like the nucleus of uranium-235, but nevertheless, it's a significant amount of energy that we can produce. This catalyzed DD reaction needs that we have to burn deuterium plus helium-3, and that needs a higher temperature in the plasma than the 3 other reactions. So sometimes a plasma would not burn the deuterium with a helium-3 if it's operated at low temperature. So in that case, we get what we call the semi-catalyzed DD fusion reaction, where the forced reaction of deuterium with helium-3 basically would not occur. So in that case, 5 deuterons produce a proton, a helium-3 nucleus, and alpha particle. Notice that helium-4 is produced here with the fusion of deuterium, whereas in the stars, the helium-4 is produced by the fusion of hydrogen. So we have a venue here on Earth to imitate what happens in the stars. We described the concept of the cross-section when we dealt with the interaction of neutrons with materials. And in plasmas, we can also use the concept of the cross-section measured here in meters squared against the temperature of the plasma or the kinetic energy of the particles in the plasma. This graph shows us here the cross-section for the DN, the neutron branch of the DT reaction. And so that would be the top one here, deuterium plus deuterium neutron branch, and the deuterium plus deuterium proton branch. You notice it peaks or operates really in the range of 100 kilo electron volt temperature of the plasma. And however, you could see that the DT reaction has a much higher cross-section and at lower energy at 100 kilo electron volts. So the suggestion here is that it's easier to achieve the deuterium plus tritium reaction. But tritium does not occur in nature, so we have to use the neutrons produced, say, from fission or from some other fusion reaction to interact with some material. In that case, guess what? It's lithium. The lithium used in our computers and our phones in lithium-ion batteries. When neutrons interact with lithium, they produce tritium. So our first generation of fusion reactors are going to be most probably, almost assuredly here, DT reactors, reactors that burn deuterium and tritium to produce alpha particles, same as the stars. And even interesting reaction is the D-helium-3 reaction. Now that reaction, as we have seen earlier, let's go back there, produces only charged particles. And we know that if you use charged particles, like here, a proton and an alpha particle, you can direct them with a magnetic field. So that reaction would be very useful in creating a nozzle, a fusion reactor that creates a nozzle that discharges the deuterium being fused with helium-3. And that reaction would be the basis of a fusion rocket that has a very high specific impulse. And in that case, we can reduce the travel time, say, for a mission to Mars from a whole year, where the astronauts are subject to solar flares and to basically deterioration of their muscle system and body system into weeks to reach a trip to Mars. An interesting aspect of it too is that the solar wind has deposited large amounts of helium-3 in the dust and the regolith on the surface of the moon. So that is the reason why we may want to go and mine that helium-3 from the moon. We get the deuterium from our Earth, and a load of a space shuttle has been calculated to provide all our needs on Earth for a whole year by a single load of helium-3 that we can mine from the surface of the moon. So that's very interesting ideas here. But once we master the fusion reactor designs using the deuterium and tritium, we may find ourselves using the D-helium-3 or the deuterium plus tritium. In that case, we may have run out of supplies of lithium on Earth. Then we depend on only deuterium plus deuterium. As I suggested, if you want to use a DT reaction, we need to produce that tritium. And lithium has two isotopes, lithium-6 and lithium-7. With neutrons produced from fusion itself, we can get the neutrons to interact with the lithium. So use the lithium as a coolant. And lithium is a liquid metal, so it would be a very good coolant for these reactors, and it would double as a coolant as well as a breeder of the tritium that we take and combine with deuterium to produce fusion. If you use neutrons as thermal neutrons, low energy neutrons, you can get that alpha particle and triton plus 4.76 million electron volts of energy but the neutrons can, as fast neutrons, can interact with the isotope lithium-7, and lithium has a higher percentage, atomic percentage of the isotope lithium-7 than the isotope lithium-6. And you can also produce tritium, but it is an endothermic reaction. It absorbs energy from you, whereas that neutron plus lithium-6 produces excess energy. It's an exothermic reaction. All right, so here we have now reactions that we can use on Earth to produce fusion, nuclear reactions. The proton branch of the DD reaction, the neutron branch of the DT reaction, the DT reaction, deuterium plus tritium, the D helium-3, we covered all of these, and the triton plus a triton is a neutron multiplying reaction. But there are other reactions there too, like tritium can fuse with helium-3, producing basically an alpha particle plus a proton plus a neutron. And even lithium-6 and lithium-7, if you create a plasma of lithium and proton, hydrogen in that case, so it's a hydrogen and lithium plasma, you would produce helium-3 and helium-4 and also produce energy, but it would need much higher magnetic fields and higher temperatures. Hydrogen and boron-11 can produce also fusion with 22.4 million electron volts of energy. Neutrons with lithium-6 and neutron with fast neutrons, on the other hand, produce tritium, and the tritium can be used there in the DT reaction. As I suggested, the surface of the moon contains helium, and other than using the D helium-3 reaction here, deuterium from our oceans and helium-3 from the surface of the moon, then you can also burn helium-3 plus helium-3. You'd be closer to what happened in the stars. You'd get 2 protons emitted and 1 alpha particle and 12.9 million electron volts of energy. So you could see here that we have an alternative to what happens in the stars in terms of producing energy on Earth. So those reactions that I've shown in the graph have cross sections that depend on the mass number of the isotope. The lower the mass number for deuterium and tritium and helium-3, you'll find that you get a cross section. If you have to design a fusion reactor, this is a reaction cross section in general, and this would be an average of the cross section and the speed of the neutron, which is a measure of its energy, an average sigma v that happens for, in that equation for the reactions, the DD reaction, DT reaction, D helium-3 reaction, TT reaction, and T helium-3. So if you are designing a fusion reactor, that could be useful material. Let us think then about fusion approaches. As I said, we try to imitate the supernovae, and we call that process the inertial confinement fusion, ICF. And that idea is being pursued by creating the conditions like a supernovae, really. So we take a little glass sphere, the size of almost like a grain of sugar or salt. You fill it with deuterium and tritium as a gas, and then you bring in laser beams, electron beams, ion beams to hit the surface of the bead made out of, in that case, glass. You evaporate part of that enclosure, and as you evaporate it, the gases are moved outwards. If they are moved outwards, they create an inverse rocket. So in that case, the little container that contains the deuterium and gas, or deuterium plus tritium gas, is imploded. It is basically brought to a smaller size. The density increases, the nuclei come together, and lo and behold, they can overcome the Coulomb repulsion that we talked about in the previous chapter, and they fuse together. And as they fuse together, they create on Earth here the equivalent of a supernova. The deuterium and deuterium, or tritium plus tritium, fuse together, and they expand, releasing their energy in the kinetic energy of the alpha particle and the neutron or the proton. One way is what's called a direct drive, in that you use laser beams and irradiate the surface of those little tiny supernovae. But another approach is to use what's called an indirect drive. So you enclose that little pellet inside what's called a whole realm or black body radiator. You add 2 windows of plastic or glass on each end. You bring in laser beams to get into the container containing a heavy element containing lots of electrons. You can bring in lasers. The lasers would interact with the surface, generate X-rays, and you fill up that whole realm or black body radiator with X-rays, and you get a more uniform, basically, irradiation of the surface of the pellet. So the hydrodynamics or become more efficient in imploding the pellet. And then the next chapter on inertial confinement, we are going to learn a little bit more about that process of implosion. And notice here that we are using a sphere. We could use a cylinder or you could use a flat kind of configuration, but the sphere, as we'll see, is the most efficient way of achieving implosion. So there are really 5 steps. You create an atmosphere, an inverse rocket, you illuminate it with a laser or electron beam or a heavy ion beam, you compress the pellet, same as what happens in the supernova that we studied in the previous chapter. You ignite the fuel and then you get a burn in the system. Another approach to fusion is to use the nature again, where the Earth's magnetic field traps the solar wind. And in that case, we try to trap the particles for a long enough time. We're going to call it the energy confinement time, and give a chance for the ions of deuterium and deuterium, or deuterium plus tritium, to overcome the Coulomb repulsion. So that includes several steps. First, you have to create what we mentioned in the previous chapter as a plasma. So you start with atoms of, let's say here, this is an atom of hydrogen, the nucleus and the electron around it. And basically you confine it into a container that is in a vacuum. You pump out the oxygen and the nitrogen out of it, so it is filled only with the hydrogen gas. Then you heat that gas inside the container. When you heat it, you impart enough kinetic energy to those electrons to be stripped out of the atom, and you end up now with a balanced mixture of ions, the nuclei of hydrogen, and the electrons, and we call this a plasma. In that case, you have a good probability that those nuclei can hit each other, overcome the Coulomb repulsion, and fuse together. Now, we don't use hydrogen, we prefer to use, obviously, deuterium. So think about those nuclei here as deuterium, or a mixture of deuterium and tritium. The problem here is that you create the plasma and those electrons and ions are moving in all different directions. They hit the wall of the container and they lose their kinetic energy. So what you have to do is create some more of a controlled environment, like in the Earth's magnetic field. And in that case, we go back to our very elementary Lorentz equation that was used in the enrichment of the isotopes earlier on, the Calitron process. And we said that the force as a vector in an electromagnetic field that has an electric field component as a vector E and a magnetic field B, acting on a charged particle of charge Q, basically is QE, meaning that the force will act on the charged particle in the same direction of the electric field. You see the F and the E have the same sign here. But in a magnetic field, the force on a particle is different. It is really the vector of its speed, or in that case, its velocity, cross product into B. So the force is going to be perpendicular to both V and to B. And in that case, if you have a magnetic field that goes in the direction of the arrow here or direction of the line, the force here is going to be perpendicular to both V and both B. So the particle is going to rotate around the magnetic field line. And that's what happened in the Earth's magnetic field when the solar wind is caught in the Earth's magnetic field and create the aurora borealis and the aurora australis. That's why we spent some time covering that material. Let us assume that we have only a magnetic field, so the electric field component is not there. And the Lorentz equation, by the way, the Europeans call it the Joule's equation, the French in particular. Then you have the force on the charged particle if you impose a magnetic field on the plasma, is perpendicular to both the velocity vector and the magnetic field vector. And in that case, it is balanced by the centrifugal force, which is mv squared over r. And that is just a reminder of your mechanics classes. So let's see what happens in a diagram. You start with a gas, as I suggested a few moments ago. You create a plasma. The plasma is contained in a container that has a vacuum in it. It would lose its energy if the particles hit the wall. But if you create a magnetic field along the cylinder, and how do you create a magnetic field along the cylinder? You surround the cylinder by coils that rotate around it. And the right-hand rule says that if you circulate a current in the direction of the arrow here, the right-hand rule, you create a magnetic field in the direction of the thumb. And so in that case, those charged particles do not touch the walls of the container. They do not drill a hole through it. They have a lot better chance of fusing together by rotating around the magnetic field line. And in that case, the ions of deuterium or tritium would move in one direction. The electrons would move in the opposite direction. And depending on the mass, you could see here that the radius of rotation, or the gyro radius as it's called, depends on the mass of the particle. So the ions of hydrogen, deuterium, or tritium move in a larger gyro radius than the electrons, which have, of course, here the radius r. The way we deduce the radius r, we took that basically we took the magnitude q over c v b and equated to mv squared over r, and then solved for r. So it gives us the radius of rotation, and you could see it is a function of m, the mass of the charged particle. So, well, there's a problem though with that linear configuration, and you can create in that the particle will start leaking at the two ends of your cylinder. So here you have coils that create a magnetic field, cylindrical magnetic field. The charged particles are in the center, and you need to contain them. Otherwise, they'll leak the same way as particles in the aurora borealis and aurora australis leaks in the Earth's magnetic field. All right, so what do? You have two choices. You can create here a stronger magnetic force that squeezes the magnetic field lines so the particles can reflect back and forth, and this is called a mirror effect. And the device that is used in that case is called a tandem mirror. But you can use another interesting process in that you take that cylinder and tie up together both ends. So turn it into the form of a torus, and the magnetic field would be in the torus itself. And you could use either magnets here, shown here, to create that magnetic field that contains the particles. Now they'll keep rotating, 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 instead of hitting the walls of the container, creating a hole through it, and or losing their kinetic energy. Or you can have just a wire going all the way around the torus and creating the magnetic field. If you use those magnets here, the device that we are going to study is called the tokamak. It was invented by the Russians, and it is the main concept used today in fusion research on how to achieve controlled fusion. The magnets here it acts basically at the basis of the transformer, as I'll show you in a moment, but there is not enough room in the center here to get the power producing equipment. We have to extract the energy and cool the surface of the container by using lithium, maybe to breed the tritium as well as extract the energy in the charged particles. But you can have a wire surrounding the process. In that case, you have more room in the center. This is a process invented by the Americans at Princeton University laboratory, and this is called the stellarator. So we have two concepts here in fusion, three concepts in fusion. You squeeze the magnetic field lines at both ends. This is called the tandem mirror, or you generate a magnetic field and basically use a transformer action to contain the plasma. We call this a stellarator, or you have a coil that surrounds the plasma. We call this the tokamak, or you have a coil surrounding the plasma, and we call this a stellarator. So these are the conceptual ideas, and we'd like to look at the engineering aspects in that case. Many different devices have been really suggested. One of them is, for instance, what's called the dense plasma focus. So in that case, you generate a plasma by heating a plasma with a magnetic field. The ions move in one direction, and basically an electromagnetic field confines them and gets them to produce fusion, and energy is released. If you use deuterium and tritium, you notice here that 14.06 is the energy of the neutron, plus 3.54 the energy of the alpha particle. So it's at 17.6 million electron volts from each reaction. We know it works. It works in thermonuclear weapons. They burn deuterium and tritium produced from lithium by the action of neutrons generated from a fission kind of a trigger of the reaction. Now we want to produce that reaction in a viable power producing device. So this is a conceptual design. We'll study it in more detail as we go along. So you create basically a fusion fuel plasma, whether inertial confinement or magnetic confinement, in the center of, say, a device. Alpha particles are produced, neutrons are produced. The alpha particle deposit most of their energy on the first wall. So you have to cool the first wall of the device, the wall that faces the plasma. The neutrons, though, are neutral, so they will penetrate any material. So you let them interact with the nuclei of a coolant. In that case, lithium is used. So they interact with the lithium, they lose their energy. Notice that the neutrons carry 80% of the energy of the DT reaction. See here, the neutrons carry 14 out of 17.6 million electron volts. So you need to slow them down into a medium that will extract the energy, and the choice medium is a liquid metal of lithium. And not only lithium, you extract the kinetic energy, but also the neutrons would interact with the lithium nuclei and produce tritium. And now you bring in deuterium from water that you would have generated through production of heavy water. The supply is the water from the oceans, lakes and rivers. And you would produce locally the tritium in the lithium coolant, and you inject both of them into the center to produce a fusion reaction. The lithium coolant now is going to extract the energy from the neutrons, maybe also cool the first wall, and you take this now to a standard thermodynamic cycle. So you get a heat exchanger, you extract the energy from the lithium, you generate steam, you take it to a conventional type of turbine and produce electricity out of fusion in general. Again, the coolant acts as a coolant, definitely, but of course, also it breeds the tritium that we need to produce our famous DT reaction. So deuterium comes from water in the ocean, tritium comes from breeding in the lithium fuel. And you could see here that pretty soon we might find ourselves running off or we may have a resource problem in the supplies of lithium in the world. They are being used extensively for lithium-ion batteries for the transportation system, but that lithium is a unique element that we can use also in electricity production in our future. There are safety considerations, of course, in fusion, and we mentioned those, but let us mention the possibility that it also offers humanity, not just in terms of electrical power production and the salting of water in the oceans from being salty to being fresh water, but also for space propulsion. The D-helium-3 reaction that you mentioned for fusion produces no neutrons. It's a neutronless reaction. It produces an alpha particle and a proton. Both of them are charged particles. So in that case, our famous equation, the Joule's equation there, can trap those charged particles because they're going to rotate around the magnetic field lines and project them in the back of a rocket. So in that case, you can create a rocket. That's a conceptualization by the Lawrence Livermore National Lab of a magnetic field created by those magnets here, where you generate a plasma. You burn the D helium-3. All the particles now are charged particles, and you exhaust them through a magnetic nozzle. And nuclear rockets, whether they use fission, where you heat up a gas like uranium hexafluoride, say, that is fissioning, or if you use fusion, would have the highest specific impulses. And you have basically an impulse that accelerates your rocket per unit mass higher than any chemical rocket in existence. So if you use a chemical rocket for a trip to Mars, it can take you a year, whereas if you use a nuclear rocket with a high specific impulse, whether it's fusion or fission, the trip would be weeks rather than years. And during a year, the astronaut's body would deteriorate, muscles and all the other organs. We know that the bones, for instance, too, and they're subject to solar flares and particles that can destroy their equipment. And you can watch some movies about that. The Russians came about an idea about a nuclear rocket using laser beams in that case. So in that case, they're using what's called an ellipsoid of revolution. I'll show you that idea in the chapter on inertial confinement that would be coming up. The ellipsoid of revolution has an interesting aspect of it, is that it has two foci, focus here and a focus here. And if radiation is emitted or sound is emitted on one side, the reflections through the walls are concentrated on the other side. So they bring in laser beams here and generate inertial confinement. On one side, the energy emitted reflects around the walls. The laser beams will come from opening here and here. Do you see that? And mirror systems reflecting the laser beams, and start a fusion on the other side. The fusion on that side will create a fusion on the other side, and then the whole thing is contained inside a black body radiator, and the radiation leaks from the bottom, and you get a rocket. So that's a conceptualization. It's a very difficult design to achieve in general. Okay, let's talk a little bit about that ellipsoid of revolution. What you can do is find your way to the Museum of Science and Industry in Chicago. If you want to save some money, so just go there on a Tuesday. It's open free for everybody. And find your way to what's called the Whispering Gallery. And then that Whispering Gallery is basically an ellipsoid of revolution, where you can stand here on that side at the focus, and a person stands on the other side at the other focus. If you whisper here with a shield between you in the center here, a whispering on that side would be heard on the other side through reflection through the walls. So that would be a basis maybe of an inertial confinement fusion system. In fact, it's used to a certain degree in thermonuclear weapons if you looked at the Coulomb-Teller configuration. The ellipsoid of revolution is some kind of also can be visited at different places. So if you visit London at St. John's Cathedral, the ceiling has a shape of an ellipsoid of revolution to a certain degree. Maybe, well, yeah, it's not a parabola, it's an ellipsoid of revolution. And if you stand at one point and you whisper, the reflection of the waves can be heard by another point, which are the two focuses or foci of the Whispering Gallery. There is also an interesting urban legend about, for instance, the United States Senate Capitol building in Washington, D.C. contains a room designated as Statuary Hall. So if you visit the Capitol sometime in your future, if you haven't done it already, well, you have to visit it again to go and look at the Statuary Hall. It basically have a reflecting ceiling that's parabolic in shape. And there is an urban legend or a tale telling us that John Quincy Adams would sit at his desk, one of the, I don't know whether he became a president, but he was one of the founding fathers of the United States, writing the United States Constitution. he sits at the desk situated at the focal point of the ceiling, and he could overhear conversations between unsuspecting subjects from different points around the room. So that was an interesting situation there, spying on his colleagues in general. All right, if you are going to design those ellipsoid of revolutions, I give you here the geometric kind of description of what's called the Cartesian oval. Basically, it follows the Fermat principles of optics, is that the time that it takes rays to move from one focus of the wall and then to the other focus has to be a minimal value. So tau 1 plus tau 2 should be equal to a minimum. And that ellipsoid, I show you the math here, basically takes a shape of an egg. So that's called the Cartesian oval. A special case of it is when it's symmetric, and this is what I call the ellipsoid of revolution that can be used for a rocket system. And it is used in thermonuclear devices that basically you have the fission device here and the radiation from it is focused on a point here that is the beginning in the Coulomb-Teller configuration of the fusion part. And basically the ellipsoid of revolution is a special case of the Cartesian oval in geometry. So if you are designing those systems, I give you the mathematical background right here. You can also create something very interesting as a hybrid between fission and fusion. What we are talking about in that chapter is fusing with a driver like laser beams or heavy ion beams or electron beams of some small pellet containing a fusion fuel, deuterium plus deuterium or deuterium plus tritium. How about something interesting is that you can use those laser beams to implode a tiny amount of fissile material and make it critical. And in that case, you take advantage of the different characteristic of fusion and fission. For instance, a single reaction in fission produces 200 million electron volts, whereas a single reaction in fusion, deuterium plus tritium, for instance, produces 17.6 million electron volt. Let's say it's about 20 million electron volt. So fission produces 10 times as much energy per reaction as fusion. So we can say that fission is energy rich compared with fusion. On the other hand, the DT reaction produces for me a neutron that has 14.06 million electron volt of energy, whereas fission produces a neutron that has a most probable energy of 2 million electron volt per fission. So here you have 2 million electron volt fission, 14.06 million electron volt in fusion. So you find that fusion is neutron rich, but energy poor, and fission is energy rich, but neutron poor. And when you get a situation like this of two systems that have different characteristics, you can always have an optimal combination of the two. So maybe in our future, may have a hybrid where fusion reactions basically compress fusion fuel, and as it compresses the fusion fuel, what is a subcritical configuration can become supercritical because the nuclei come close in together. So this is left for those of you who are looking for interesting topics to research for maybe master's degrees or PhDs in general. The technical demands on a DT fusion plasma neutron source are lower by more than an order of magnitude compared to those of a pure fusion system. In that type of an optimal configuration, you can be a factor of 10 closer to achieving fusion in our time and not have to wait 50 years in the future to have fusion. And if you develop that kind of a hybrid, then you can learn about how to eventually design and build pure fusion devices in the long term. The reduction by a factor of 10 in the energy comes from the fission event being 200 million electron volt and the fusion event being 17.6 or 20 million electron volt. That's a factor of 10 in the energy release per as a ratio of a fission reaction relative to a fusion reaction. So this reduction in technical demands is thought to lead to lower cost and feasibility for a fusion-fission hybrid as compared to a pure fusion or pure fusion systems. And that basically gives us a neat introduction about the possibility of using both fission and fusion together. I am back to the chat room if you have questions. Otherwise, we'll use up our time and start on another chapter. No questions, so we start another chapter. We won't waste our beautiful summer time here. So we go back to the share screen and we covered so far in fusion two topics: the plasma and fusion reactions and the fusion concepts. Then we come to inertial confinement fusion now and learn a little bit more detail about it. Remember that inertial confinement fusion is an imitation of what happens in the stars. This is another picture of a supernova where the stellar or the fuel in the star, whatever it has burned to through the process of nucleosynthesis, carbon or silicon burning. And this is what we do in the laboratory here on Earth, where fusion is occurring. Notice that most of the universe is a plasma where fusion is occurring. And what we are dealing with is learning really about the universe itself and the natural phenomena and applying them for our technological society. Another revision here in inertial confinement, you start with a pellet of glass, the size of maybe a grain of sand. You include on its inner surface deuterium plus tritium, which is hydrogen gas. You use some driver electron beams to create an atmosphere, create practically an inverse rocket. If you evaporate the surface, the gas is moving out here with those arrows, push the pellet on the center in and implode it. So that's a process of implosion. And this is what we call the directly drive laser fusion event. So you find that once you bring the nuclei and implode them close together, they fuse together, they explode. And in that case, the energy that it was in the deuterium plus tritium reaction or deuterium plus deuterium is released as kinetic energy and X-rays and gamma rays, and the pellet basically expands, and now we build some enclosure, a nuclear reactor to extract that energy. So we have the direct drive that I have shown you here, or the more advanced idea is the idea of the soft X-rays, or what's called the indirect drive, or the whole round. That's a German for a black body radiation. So in that case, the pellet is enclosed inside another container that has a window, a plastic window or a glass window. You bring in laser beams, you don't hit the pellet. You hit the walls of the container, the whole round. X-rays are generated, they fill up the whole round, and the X-rays now give a uniform irradiation of the pellet. So the surface starts evaporating, and as it evaporates, it creates that inverse rocket. It compresses the pellet. You could see it here becoming smaller, and then fusion is induced, and the pellet itself, it destroys the outer container, but the energy now is released as an alpha particle and a neutron in the case of the DT reaction. Some people have been even trying to do research on not having multiple beams, but creating an atmosphere with multiple beams initially, and then sending a large beam into the created atmosphere of a plasma around the pellet that would supposedly implode it. That hasn't been tested, but has been studied theoretically in general. Now, that means that we have to study in the remaining few minutes here the implosion process. So what happened in the implosion process? And in that case, we use the laws of hydrodynamics, of fluid mechanics. And in that case, we know that in fluid mechanics, we usually apply several conservation laws. In fluid mechanics, we apply conservation of energy, we apply conservation of momentum, we apply conservation of mass, and then we couple all of this by an equation that includes an equation of state. Let us just apply here today the conservation of mass constant, which is in mechanics also called the equation of motion. All right, so let us take different geometries. Let's take linear compression. So we take a flat little a plate of a material that we are going to compress, whether it's a fissile material or whether it is a fusion material, deuterium and tritium. Now, if you get a little mass as a flat mass, maybe a flat disk, you'll find that the mass has to be conserved at the time before you compress it as the time after compression. So the mass is equal to the density multiplied into the volume. So I'll say here that V sub 0 multiplied into rho sub 0, that's the mass of the material. It cannot disappear. It will be the same after I compress it. So we are going to compress it to bring the nuclei together and have them overcome the Coulomb reaction and fuse together. So if you take a flat surface, like a little plate maybe, the volume is equal to the thickness of the plate multiplied into the area. And that area has to remain the same after compression, but the radius or the thickness now, after you compress it, is going to be increased. And the density is increased, so the radius will be decreased. So if you cancel A and A from both sides, you find that the product of rho r, and if you do research on inertial confinement, you find that the rho r value is considered all by itself. If you simply use the scissors, the inverse scissors rule, I can write an expression of rho, the new density, relative to the old density, is equal to the initial radius divided into the new radius. Now the density could be, say, density of water, 1 gram per cc. And if I reduce the radius by a factor of 10, so the new radius here would be 1, the old radius would be 10, you'll find that I can increase the density by a factor of 10. All right, now let's think about, instead of a flat kind of surface, we have a cylindrical surface. Well, in a cylinder, the mass is going to be conserved also, but now the cylinder would have a length capital L, and the cross-sectional area is pi r sub 0 squared. Before compression and after compression, it's L pi r squared divided into the rho. So remember here, we're applying one of the laws of fluid mechanics, which is a conservation of mass. L and pi cancel from both sides, and you end up again with that rho r vector value. But in the cylinder case, it is not rho r anymore, it's rho r squared. So if you look at the density after compression, the thickness of the radius of the cylinder, instead of being, say, the density increasing by a factor of 10, oh, it is now 10 squared. And in that case, you can increase the density of the cylinder by, say, if the radius is reduced by a factor of 10, you increase the density by a factor of 110 squared. And better even just plain geometry, just playing with the geometry and conservation of mass. If you have a spherical kind of a pellet, like I've shown you earlier, the volume is 4/3 pi r naught sub 0. That's the volume of a sphere multiplied to the density of a sphere at the beginning of the, before the compression, should be equal to after the compression. 4/3 pi cancels with 4/3 pi, and the rho over rho sub 0 is r naught over r. Oh, now it's the third power. So if you reduce the radius by a factor of 10, so here this is r sub 0. Let's take it initially 1 centimeter, and 10 let's take it 1 centimeter. If it's 0.1 centimeter here, if you reduce the radius by a factor of 10, look here, you can increase the density by a factor of 1,000. 1,000. cylindrical flat geometry, a factor of 10 becomes a factor of 100 if you use spherical geometry. It becomes a factor of 1,000 if you use spherical compression. So in the same way that that implosion process is used in fission devices or fission weapons, especially when you implode plutonium. Think about the first two chapters. The spherical geometry of the plutonium sphere would have been reduced by maybe a factor of 2 or 3 only. But in general, the density can be increased by a factor of the reduction of the radius. If the radius initially was 10 and later on it's reduced to 1, 10 over 1 cubed could be the case of a sphere. So we take an example here of a three-dimensional system here like spherical, and you only reduce the radius by a factor of 1/2. You find that in that case, the density would be increased in the spherical system by a factor of 8. And if you reduce the radius of a sphere by a factor of 10, your density now can be increased by a factor of 1,000. That's why fusion pellets designs use basically spherical geometry. And this is an actual pellet, laser pellet. It's surrounded by some kind of a Saturn rings. The lasers heat up those rings made out of gold. In that case, it's an experiment. You have a tube that brings in the deuterium, tritium gas here, mixture, and it also holds the pellet. And these are gas-filling tubes, and you irradiate the pellet with laser beams, the X-rays, and the laser simply can implode the process. This is an indirect drive pellet. You could see the cylinder here with the pellet in the center. The laser beams come from windows from both ends, hit up the walls, generate X-rays, and implode the pellet. This is another form that they call the basically wagon wheel, where the pellet is hung at the center, and the interior of the wagon wheel is irradiated by lasers to create the soft X-rays for imploding the pellet. So this is a design of an actual pellet. It's a very tiny little thing here that's 5 millimeters, half a centimeter in size, with the pellet hanging in the center, with a window for the laser beams to come in and hit the walls. Basically, it's a plastic window. So the laser beams hit the walls here, create a whole realm X-rays, and that is basically what implodes the pellet, soft X-rays, in the same way as it happens in thermonuclear devices. Really, the thermonuclear part of the device is imploded with soft X-rays. This is an X-ray picture actually of those laser beams hitting the walls of a pellet, and experimentation is going on. This is the point where the laser are hitting the interior of a whole round pellet in general. So this is again studies on how to design those pellets. It is not just the idea of creating the whole round. People have been experimenting with a double shell target. So in that case, you get a target here containing the fusion material, and on the outside you have another target. So you accelerate the other targets to hit the inner one. So it's like having an anvil and using a hammer and hitting the anvil. In that case, you transfer the momentum from the outer shell to the inner shell, and you can get better compression. The idea here is to achieve compression of the pellet. Different foams are used for levitating the pellet, like polystyrene, aerogel. Aerogel is a lighter density than air. Silica aerogel, silicon, which is really silicon oxide, divinyl benzene. These are all chemical kind of components that are used in those experiments to center the pellet so that it can be irradiated by the laser beam. If we are going to build the fusion reactors in the future, right now, gold and gadolinium are used in those pellets experiments, but in the future, we may want to use lead as a material for the construction of those pellets. Lead, of course, is much cheaper than gold or gallium in general. And when we use the drivers, what kind of drivers do we use for imploding those pellets? Basically, we can use heavy ion drivers, like that's a Lawrence Livermore National Lab, diode pump solid state neodymium lasers at the Lawrence Livermore Lab again, Lawrence Livermore Lab. The United States Naval Research Lab, NRL, uses krypton fluoride lasers. Sandia National Laboratory is a Z-pinch X-rays. Basically, the University of Rochester have experiments, and General Atomics Company in San Diego, California, also is carrying experiments. So I'll go very quickly over these for another minute here. This is the heavy ion beam driver accelerator at the Berkeley lab. Notice the size of it, the gentleman here standing here performing maintenance on it. This is the important aspect of the work in the United States. This is under construction and now finished, what's called the laser ignition, the National Ignition Facility. They're trying to achieve ignition, or basically the nuclear process of inertial confinement fusion, producing, in that case, more energy than the energy in. So this is not pie in the sky. You'll find that all countries, industrialized countries, have similar facilities. France has one, Russia has one, and the goal is to achieve fusion energy in our future. I'll stop at this point, and I'll finish that chapter next time, but I'll stop the sharing, I'll stop the recording.